In this lesson, we will be talking about a very important concept of stationarity, and we'll also be discussing about weakly dependent series. Let's begin by recalling our understanding of time series data. We know in time series data, any value at time t is some function of previous data. However, most real-world time series data, including stock price, weather pattern, network traffic, retail sale, is stochastic in nature. A stochastic, any process which is influenced by randomness. So the future value depends on both some deterministic component plus some random component. The stochastic process is unlike deterministic process where we can decide the future value, we can predict the value with certainty based on certain relationships or formulas. Now let's have a look at what makes a time series a stationary time series. To have a stationarity in time series, there are three conditions which are required to be met. 1. It has constant mean across the time, that is, its expectation or mean is constant. It is not changing with time, it is not a function of time. Now, the second condition is that the variance of that time series is also constant, again, not a function of time. And the third condition is that the covariance between any two legs at particular time t and lag xt plus h is only a function of the relationship between those legs and not a function of time. So in a nutshell, we can say stationarity refers to a time series whose statistical properties such as mean, variance and autocorrelation remain constant over time, and it is critical for time series forecasting models as they assume the input series is stationary. We will dig deep into this and each of these conditions to understand what makes a time series stationary and also why do we care about it. Let's have a look at one more concept, which is weakly dependent time series. So if we have any time series xt, and let's say this is time t and this is time t plus h, correlation for a weakly dependent time series, correlation between xt and any xt plus h tends to 0 for h tending to infinity. What it means that as we progress in the future, the relation between current lag and the future values become weaker. This means a series is weakly dependent time series. We'll be talking about the examples, moving average and autoregressive in detail in our future lessons. So first condition is stationarity in mean, which implies that expectation of any time series xt is constant. So let's say x is a variable which depends on time and we have, let's say, this time graph. Now visually we can make out the process does not have a constant mean. It is growing with time. And so in this situation, this condition is violated. Now let's have a look at another time series where a variable xt again depends on time has this time series structure. So visually you can make out that even the process is deviating but it stays around some constant mean mu. So in this situation we have this condition satisfied of a constant mean in time series, and we can say that the process is stationary for mean. Now let's see why do we care about stationarity in mean for it to come up with a reliable forecast. In time series statistical models, we often try to establish a linear relationship between the current value of the variable and its lagged value. And this approach treats the lagged value as explanatory variable and the current value as dependent variable. So let's say we have a two time series. One is dependent variable, which is yt, and the other is explanatory variable xt, and we are trying to establish some linear relationship between these two variables, where epsilon t is some random error or fluctuation at instance t. Have a look at these two graphs, where in one case xt, which is explanatory variable, is a stationary series and yt is non-stationary, and in another case, this one, both xt and yt are non-stationary. In both the cases, if we observe, the gap at any point of time t between xt and yt is varying. If we want to establish a linear relationship over here, we can have beta again as a function of time t, but in that case we will struggle to find how xt is impacting yt, and it will not help us give us a reliable forecast. So we need to have a constant value of beta in our order to establish a linear relationship, and if any of the series is non-stationary, we will not be able to come out with a linear relationship. Now let's have a look at this graph, where we have again two time series xt and yt. Yt is dependent on xt, and these are stationary time series in the sense they have some constant mean. So if we observe at any point of time t, the distance between xt and yt remains constant, and we can come up with some sort of linear relationship in this case, where yt is dependent proportionally on some value of xt plus some random error, and that is how stationarity in mean becomes the base assumption of statistical models like ARIMA models, which come up with a linear relationship between current value of a variable with its lagged variable. Let's talk about the second condition of stationarity, which is constant variance, which implies series to be stationary. The variance of any time series need to be constant. Here in this time series, though we have a constant mean, but the fluctuations around it is varying as per time. Or we can say that variance of xt is some function of time, and hence it violates the second condition of stationarity, which is variance should be a constant. And so this series is non-stationary visually. And if we have a look at this time series, where again a mean is constant and also the fluctuations around the constant mean is constant, this is an example of stationary time series satisfying the second condition of constant variance. Let's again take example of two time series, where one is dependent variable yt and the other is explanatory variable xt, and we are trying to establish a relationship, linear relationship between these two variables yt and xt, and we want to come up with some constant beta. If at least one of the series is non-stationary and it has some variance which is not constant, we would expect yt also to have some variation if there is a relationship between xt and yt. And in this case, our beta again cannot be constant if the variance is not constant. And now let's have a look at this graph, where both the time series seem stationary in nature with respect to variance. Any fluctuation in xt will lead to fluctuation in yt, which is constant. And here in this case, we can establish a linear relationship between these two variables. And so we need to take care of constant variance in case of statistical forecasting models. And so we have discussed two conditions for now. One is constant mean and constant variance. And now let's talk about the third condition, which is covariance for stationarity. In this figure, we have two time series yt, which is a dependent variable, and xt, which is explanatory variable. here the variance between the legs is constant and is independent of time. And that is the third condition of covariance stationarity, which implies that covariance between variable at current time t and its lag value is a function of the lag and not the function of time. So if we have a look at the series 1 over here, we will see that the distance between the lags remains constant, independent of time. Well, if we have a look at series 2 and if we try to identify the relationship between the lags, let's say we have lag xt and xt minus 1. In the left side of this figure, we might have relationship like this, xt minus 1 plus something, while here in this side relationship between the lags will change, maybe minus 0.5 plus c. And so this series violates the condition of covariance stationarity while this remains appropriate. Many statistical models require the assumption of covariance stationarity to simplify parameter estimation. So these are the three conditions for stationarity which should be met altogether to make a series stationary, and it is the basic assumption of statistical model to come up with a stable linear relationship and reliable forecasting.